So in a previous video, we looked at what happened when we plugged this square wave forcing function into this RC filter, and we used the Laplace transform to find the exact solution for the voltage at that node right there, V of t. And when we did that, we found that the exact solution looked something like this. It was off until time equals 0, and then after time equals 0, it sort of gradually grew a little bit and sort of bounced around like that. But now in this video, we're going to look at a little bit more of a useful way to look at this problem from an electrical engineering perspective. So instead of finding the exact solution, in this video, we're going to look at a way to isolate the steady state solution of this system. So we're actually going to take the Fourier transform of this forcing function here, this f of t, and then we are going to apply the method of phasors to the forcing function, and that's going to give us the steady state voltage at that node. So if we do our work correctly today, then what we're going to find is the steady state solution, which basically is the long-term behavior of the system. So eventually, it starts off totally, deviating from the exact solution because it's always our steady state solution is basically always on. It's on when it's not supposed to be over here in the negative side of the negative side of the time axis. But eventually, as time gets really large, as time goes to infinity, the exact solution, the green curve here, is going to converge to the steady state solution. And if that happens, relatively quickly, then, we really only care about the steady state solution. So we're going to go ahead and try to find this steady state, the steady state solution of this system. So the first step is to extend our forcing function so that it is periodic. And I know you think it already looks periodic, it's this repeating square wave, but it's certainly not periodic for time is less than 0. So we want to make this, periodic all the way back in time as well. So it's got to look something like this. We're going to extend it. And then because we've now turned it into a totally periodic signal for all time, it just keeps repeating over and over for all the way back in time, all the way forward in time. It's these square wave pulses. We can now take the Fourier transform, or find the Fourier series for this forcing function. And so what does that mean? Well, the Fourier series is a way to represent truly periodic signals in terms of harmonics, which are integer multiples of the fundamental frequency. So first of all, let's take a look at what the fundamental frequency is of this forcing function. We see that it has a period of t. We see this right here, it repeats every t time units. So the fundamental frequency, or I guess in what I'm, what I should be saying is the fundamental angular frequency. This is going to be 2 pi over the fundamental period, which is that t time units. So this is our fundamental frequency, and so then we should be able to represent that function in terms of our upper harmonic. So we have some constant here, plus we have this sum of all these different harmonics. So we're going to have these coefficients of the cosine of the whole number multiples of this fundamental frequency, and then we have the sine of these whole number multiples of this fundamental frequency. So this is how we're going to try to find, this is how we're going to try to represent that signal f of t. And our goal is then to find these coefficients, a0, an, and b of n, that can be used to, put those harmonics in the correct ratios and, mix them up in a big recipe and add them together so that they actually do form f of t. So, if you take, some sort of signal class, uh, you'll learn that the this first term here, this a sub 0, this is going to be just equal to the average value of the function of interest over one period. So it's just going to be the integral over one period of f of t dt, and then you divide by the period. That's the classic definition of the average value function. And then also, based on orthogonality, you can also then use the following formulas for to find these coefficients. So the cosine coefficients can be found using the following formula. You take f of t, and then you take cosine of that term there. Perfect. So that's what you got to do to find those. And then similarly, these sine coefficients can be found in the exact same way. Perfect. So let's go ahead and find our a sub 0 term first. So if we go and look at this this function here, let's just use our reasoning to find the average value. So we see that over the course of one period, how much area is enclosed by this signal over the course of one period. Well, we see this whole block here, which is going to have base t halves, and then it's going to have height k, and then that's just the total area enclosed by one period. And then let's divide then by the length of a single period, which is just going to be divide by t. So if we then cancel these t's, we find that the average value over a single period is just k over 2, which makes sense. The signal is reaching a height k, but it's only doing that half the time. Half the time it's at 0. So k over 2 makes perfect sense for our 0th term. So we got k over 2 for our 0th term. Now let's move on to finding a sub n and b sub n. I'm just gonna go ahead and spoil this for you. All the a sub n terms are going to be 0 because this is a quasi-odd function. And then, but if you wanted to go ahead and try to solve for the a sub n terms, you can go ahead and use this formula. You're just gonna be doing unnecessary work, and it will just lead you to the answer of 0 for all of them. So you can go ahead and prove that to yourself if you want to, but we're not going to waste time doing that. So you can go ahead and do it though if you're interested. But now let's take a look at the b sub n terms. So we have 2 over the period. Let's integrate from 0 to t, a whole period, and then we're going to take this sine of n. And then instead of doing omega naught, let's plug in the actual definition of the fundamental frequency, 2 pi over the fundamental period, dt. And then instead, let's also manipulate this limit because the pulse is only on until t over 2. So we can really just take this integral from 0 to t over 2 instead of from 0 to t, because this whole portion is just 0, so it doesn't really matter. So let's instead go from 0 to t over 2, and from 0 to t over 2, f of t is just equal to k. That's just how a square wave works. So let's go ahead now and find the antiderivative here, b of n, or b sub n. it looks to me like the antiderivative of sine is negative. Cosine, keep those internal guts of this. And then whenever we take the antiderivative, we also have to remember to multiply everything by the reciprocal of the coefficient of whatever is in the argument here. So this is our coefficient in the argument. Let's multiply by the reciprocal there. So there we go. And then let's also remember to keep our limits of integration 0 to t over 2. Let's also do some simplification here. I know I can cancel these big t's. I can cancel those. And it seems like I'm left with negative k over pi n. And then I have, cosine of 2 pi n over big T times little t evaluated at those limits. So let's just plug in our limits now. So we're going to get negative k all over pi n times cosine of 2 pi n over big T. We're going to plug in t halves, and then we're going to subtract our evaluation at the second limit. So this is then going to be cosine of 0, plugging in 0. Remember this double negative because one subtraction comes from the evaluation, and then one subtraction sign one minus sign comes from just that minus sign right there. So perfect. Now let's cancel some more stuff. Those 2's cancel, those t's cancel. And it looks like then if we also convert these minus signs into a plus, and then we flip the order of the terms, and also just remember that cosine of 0 is 1, so this doesn't really matter, then it looks like this is our final answer. We just have 1 minus cosine of pi n. Boom. And then I'm also just going to use a little trick from high school calculus, a C in AP Calculus C. You learn that for, if n is restricted to integers or whole numbers, then cosine of pi n just behaves the same as negative 1 to the power of n. That's just a little trick you can use to get rid of the cosine, because I think it's easier to think about it like this. And then let's just think about the different cases here. So if n is even, like 0, say, then when you plug in an even number for n, then this is just going to equal 0, right? Because it's going to be like 1 minus 1. But then if n is odd, then basically this, like 1, then if we plug in 1 for n, then this negative sign here can pass through the odd exponents. So it's actually going to end up being 2k because, let's actually just do that a little bit more explicitly. If you plug in an odd exponent here, then our coefficient b of n is actually just going to be k over pi n, and then this negative sign here can pass through odd exponents. So you're going to get this, then your b of n coefficients are going to have this 1 minus negative 1, which is going to give us a 2. So if n is odd, then our b coefficients are 2k all over pi n. So let's then go ahead and, now that we've solved for our b coefficients, let's go ahead and, make this synthesis. So we're going to put this together and represent f of t using this summation notation. So we're going to go ahead and say that f of t is going to equal, what was our a sub 0? That was, remember, just k halves, k over 2. And then we're going to take this from n equals 1 to infinity, infinitely many harmonics. Then remember that our cosine coefficients don't exist, so we get rid of all the cosines. And then all we have left is our b sub n coefficient. So we have k over pi n times 1 minus negative 1 n. And then this is all going to be multiplied by sine of n times the fundamental frequency times t. But then instead, again, let's just remember to write in the real definition of the fundamental frequency, which is 2 pi over big T. And then actually, sorry, I'm being kind of weird about the notation. Let's just put the 2 pi in the front. So this is our Fourier representation. We can also simplify this just a little bit, because remember, we know that basically all the even values of n, don't really even matter. They don't, they don't contribute anything because they just collapse to 0. So we don't even really need the even terms. We can just instead focus on the odd terms. So we can instead just write this using only the odd coefficients. So everywhere I see an n, I'm actually going to write, I'm going to replace it with 2n minus 1 to ensure that it is an odd integer. So that's going to just go ahead and make sure we only focus on the odd components. And if I do that, then all the coefficients just need to be 2k over pi times that index. So instead, let's just write 2k over pi times our odd indices. And then remember, we also need to only care about the odd indices inside our sign as well. So this is just a way to simplify a little bit because, we're just, getting rid of the even indices and just making sure that we're focusing on the only terms that are, really mattering. Okay, perfect. Now let's go. Now that we've represented this system in terms of only pure sine waves, let's go ahead and think about how we can apply the method of phasors to this analysis here. So in our RC circuit, remember we had a resistor here, we had some sort of capacitor here, and then we were measuring the voltage right here. So let's think about what would happen if we plugged in a purely sinusoidal, some pure cosine or sine wave as the forcing function here, instead of some, weird pulsing step function like we were doing originally, or some weird pulsing square wave. Well, then we could use the method of phasors to solve for this. So we could, turn this phasor into a complex number. Remember, we can write pure sine waves as their amplitude times e to the imaginary unit times their phase offset. And then we could also rewrite these circuit components in the phasor domain too. So the resistor would remain unchanged. Capacitors are represented as 1 over the imaginary unit times the frequency times the capacitance. And then let's just replace that with a capital V, just so that we're all clear we're in the phasor domain. And then we could go ahead and solve for a V here. So using the voltage divider rule, we know that the voltage at V is going to equal, all the resistance that's downstream of it, 1 over j omega c, divided by the total resistance, which is 1 over j omega c plus r, and then times the total voltage. So this is AE to the j phi. So this is just classic voltage divider equation. You could look that up online if you forgot it. So perfect. Now let's multiply the numerator and the denominator by j omega c. So that's just going to clear the numerator, and it's going to really simplify the denominator well. Perfect. And then we just have this in parentheses there. I've highlighted that we just have some complex number, and then we have another complex number multiplied by it on the right there. So let's write that first complex number, 1 over 1 plus j omega rc, let's write that instead in terms of its magnitude and phase. So let's, you can write all complex numbers in their Cartesian form, a plus bj, or you can write them in terms of their magnitude and their phase using the complex exponential, as I've done with the one on the right. So let's just put them both into, magnitude phase form and write them using the exponent e. So let's multiply the numerator and denominator now by the complex conjugate, which is going to be 1 minus j omega rc. So let's multiply by the complex conjugate. That's going to give us 1 minus j omega rc in the numerator. And then in the denominator, we're going to get 1 minus j squared omega squared r squared c squared. That's based on the definition of a difference of two squares. And then j squared is, of course, -1. So this is just going to turn into a plus sign. Perfect. And then remember to keep that over there. And then now that this complex number in parentheses is in a little bit of a nicer form, we can go ahead and find its magnitude and phase. So the magnitude is going to be the real part squared plus the imaginary part squared, and then all under square root sign. And then we can also just multiply by this constant, constant factor in the denominator at the end to just, because that can sort of, whenever you're finding the magnitude, any sort of multiplicative constant can just sort of pass through until the end. So it looks like the real part of this number, if we ignore that multiplicative constant in the denominator, the real part is just going to be 1. So let's just, as we're finding the magnitude, let's just put a 1 squared there. And then we want to add in the imaginary part squared. Well, it looks like the imaginary part of this number is negative omega rc. So we're going to square that. And then now that we've put that all under the square root, that's how you find the definition of the magnitude. Let's then correct by bringing in this multiplicative constant. So we want to then make sure that we divide by what it was originally divided by, which is 1 plus omega squared r squared c squared. And then you'll also notice, though, then that if we distribute this 2 and cancel out this negative sign, let's distribute this 2 exponent, because exponentiation distributes over multiplication. We basically have, the square root of x over x, which is just equal to 1 over the square root of x. So this just simplifies really nicely. So the magnitude of this is just 1 over the square root of 1 plus omega squared r squared c squared. So that's perfect. This is our magnitude. So the magnitude of, not the magnitude of v, but the magnitude of this number in parentheses here is equal to that simple thing. And then let's find the phase. Well, the phase is going to be the arctangent of the imaginary part of the number divided by the real part of the number. So the imaginary part was this, the real part was 1, and we also can just ignore that multiplicative constant entirely, because it would just cancel out in the numerator and denominator inside the arctangent argument. So we can just totally ignore that thing circled in red when we're thinking about phase. And now that we have this arctangent for the phase, it's also important to think about if we need to add in any sort of correction on the unit circle, because arctangent has a restricted range or restricted output. But it turns out, because our imaginary part was negative, and our imaginary part is negative omega rc, and our real part here is positive, it looks like we are in the fourth quadrant of the unit circle, and our angle is just going to be some, negative angle. So, our phase is going to be some negative phase, and this is the 2 quadrants of the unit circle, the quadrant 1 and quadrant 4, where its arctangent is not restricted to go between. So perfect. We don't have to worry about any sort of restrictions on the output of arctangent. So it looks like our phase is just perfect. It's equal to arctangent of negative omega RC. And arctangent is an odd function, so that negative sign can pass through odd functions. So we can just pull the negative sign out front. And so perfect. Now let's just rewrite this complex number in parentheses in terms of, in terms of the magnitude and phase, the phase representation of complex numbers. So we take its magnitude, and then we take e to the power of j times its phase, which is this. So we've just found another way to represent what was originally in those parentheses. And then let's now just still carry along this a e to the j phi, and then this, if I can highlight this, I'm going to move this over, and this is still equal to v. And I also don't mean to confuse you. I guess I'm using the Greek letter phi twice there. So this is supposed to be the phase of that complex number, and this is the magnitude of this complex number. And this phase here is just some arbitrary phase of whatever arbitrary signal, arbitrary phasor we plugged in as the forcing function initially. So sorry, I didn't mean to use that symbol twice, if that was confusing. So now this is our big capital V here, and then let's just use exponent rules to combine this. So if we could just further simplify the V term here, the terms that make up V. So exponents add here. So or the exponents add if there's the same base. So we just now basically are left with this, and this is like pretty simple stuff here. So we can see that whenever we plug in some phasor that's equal to a times e to the power of j phi, the filter is going to give us back out a signal which has its magnitude attenuated by a factor of 1 plus omega squared r squared c squared. So it divides it by this factor in the denominator here. And then it also gives it a phase offset of negative arctangent of omega RC. So this is how this filter transforms signals. We've just found out exactly how it transforms signals, with our analysis. And a fun fact is that if we chain together or add together multiple different signals and pass them through this RC filter, this RC filter will behave linearly. And so the output here is just going to be it's going to apply this transformation to all three of these input signals, and then it's basically just going to add them together. It's going to add all those transformed signals together, and that will be the output. So this transformation is basically a linear transformation, because all it does is it applies this magnitude change and phase change to all of these sinusoidal signals, and then it adds together the results. So it's a very linear thing. And that's perfect, because what we saw is that the signal we are inputting, this f of t, even though it doesn't look like a purely sinusoidal signal, it can be represented, as we've shown, using purely a sum of purely sinusoidal waves right here. And so therefore, we can use that linearity property to apply the transformation to each of those signs individually, and then we can add the results to find how the filter will actually behave. So this is perfect. We can just apply this transformation to all these individual harmonics, and that's how we're going to get our final answer. So if we just go ahead here and paste this whatever this is called, this Fourier representation of the forcing function right there, we're now just going to go ahead and apply to each of these terms this transformation here, this divide by that factor and phase offset by that much. So let's write our final solution v of t. And now let's think about, first of all, how this transformation is going to affect this dc constant term, this k over 2 term. So this is a term where omega equals 0. And so if omega equals 0, we see that's if we were to pass this DC signal through this transformation, if omega is 0, then we're just going to end up with a over 1 plus 0 squared e to the j phi minus arctangent of 0. Well, arctangent of 0 is 0. This goes away, so we're just still left with a times e to the j phi. So basically, constant terms where omega equals 0 for them, they have no frequency, they can just pass through unscathed. And that should make sense to us because this is basically a low-pass filter. This is a low-pass filter. And so basically that means that signals with incredibly low frequencies, such as frequencies of 0 or omega is equal to 0, should just be able to pass through unscathed. So that should make a lot of sense to us. So this term, this k over 2 term, passes through unscathed. We just keep it. Okay, now we do need to, the rest of these terms do not pass through unscathed. So let's go ahead and write the magnitudes of these waves here. So these are the initial magnitude of the wave, these 2k over pi times 2 to the n minus 1. That's the initial magnitude of the wave. But now, remember, we have to now divide by this corrective factor here. So we're going to multiply by the reciprocal of this corrective factor. So we're going to get 1 plus omega squared r squared c squared, and we'll come back and talk about what omega should be there. And then finally, let's inside the parentheses here, let's also make sure we correct by this phase offset here. So we have the original stuff right here. It's 1 over t, but then we want to make sure we subtract this phase offset here, which is arctangent of omega rc. Okay, so this is basically our final answer, but we haven't really answered what this omega is. And so the omega we're talking about is actually just going to be the omega of these individual, it's the omega of each individual harmonic. So each harmonic that we're using has its own multiple of the fundamental frequency. So it's literally 2n minus 1 times the fundamental frequency. And so that is the frequency of that harmonic, this whole thing. And so this whole thing needs to be plugged in wherever you see omega, because that defines, it's the frequency of the signal defines how the signal itself is transformed by the filter, because it's a frequency dependent filter. So let's go ahead and just plug those in, and then that's going to be our final answer. So this thing right here, this frequency defines the transformation. So let's plug it in. This is actually going to be maybe we're not going to have room to actually plug it in to write it down, but let's just write here that let's just replace this with, let's just write omega there, and we're going to bring this over. And then let's just write here below where omega is equal to 2n minus 1, the odd integers or odd whole numbers, times the fundamental frequency. So this is our final answer here. This is going to give us the steady state solution for our problem. So if you were to go and plug this in to Desmos, you would find that this truly does give you the steady state solution, which is what we are looking for. It's going to give you this blue curve right there. So let's actually go ahead and look at Desmos. So this is, first of all, let's turn on our Fourier series. So this is the Fourier representation of our square wave, our input signal. So this is just the square wave that we were initially inputting, represented as a sum of sine waves, and you can see this here. It's represented as that sum of odd sine harmonics. So that's perfect. Let's see if I can move over so you can see it's just a very simple equation. It's just those odd sine harmonics, just like we found, and I've just chosen arbitrary values for both k, which is the height of the height of the function, so k equals 3 here, and then I've also chosen an arbitrary value for the period, big T, which I think is also 3. So that's just arbitrary. So then let's take a look at the exact solution. Let's turn this on. So the exact solution was something that we found in a previous video. So you can see that this is truly the voltage at the node of interest because it is off for, t is less than 0, which is what we wanted. And then it turns on and it gradually grows. So it has this sort of transient behavior at the beginning. But what we've now found is this steady state solution, which, let's turn this on. Now, this is what we found today, which is basically, it's more valuable than the exact solution because, as you can see, the exact solution quickly converges to this steady state solution right there. So, it's even more valuable. And as you can see here, we now through this method have the steady state solution written in terms of, pure harmonics or pure sinusoidal functions. So we have this, sinusoidal decomposition of the steady state solution. But it's, of course, not accurate for small times and times less than 0. And then also, let's just see here quickly. You can see here what happens when we play around with the arbitrary values I've chosen. So you see here we can change the period of the input signal. That's going to change the period of everything, make everything longer. Let's zoom out here too. That's going to make everything longer. We can make the period smaller or shorter. We can change the scale everything by the a constant k. K was just the height of the original pulses, so that's just gonna scale everything. That doesn't really make that big of a difference ever. But we can also change here. This is important. We can change the resistance of that was in the filter. So if we make this resistance really high, you can see that then maybe the exact solution does start to matter because, as you can see, it takes the exact solution a long time to build up to meet the steady state solution. So that's important. And then here's the capacitance. You can make the capacitance really small or, whatever you want to do. Then if the capacitance is really small, then, basically there is no difference between the input wave and the output wave. So that's pretty interesting. There's all these different relationships that, you can play with. So this is all, pretty powerful stuff, these filters. And as you can see, we now have this representation of the steady state solution.